physics series. We're going to finish off the lesson radioactivity that we started on Thursday. So on Thursday we did alpha decay, which is shown here on page 25. We'll just remind you of a little bit of things here. Okay, we're good about that. I'm going to just be putting the hazards for radioactivity. The hazards are how far they can travel in air. So really this little line here should actually go up here. We won't read too much about it now. We'll just kind of carry on with the other radiation. Okay. So on the next page, which is page 26, we'll talk about beta negative decay. Okay, and there's two different types of beta decay, and there's subtle differences between them. So beta negative decay is a negative beta particle, which is a really high energy electron that's emitted at high speed. Usually the speeds that they're emitted at are very close to the speed of light, and that would be emitted by an unstable nucleus. What happens in beta decay, or the algorithm for beta decay, is we have our parent nucleus, so A, Z, P. Again, remember to draw the arrow right after the parent nucleus, and then you're going to draw the beta particle. And the beta particle can be represented two different ways. The A is 0, and the Z is -1, because it doesn't, like well, we'll talk about where that -1 comes from in a minute. Okay. And then you can use beta, like B. You don't have to put the negative sign like you did on the previous page, because we had the negative with Z. And then the other thing, sorry, I just want to say you can also write a 0, -1 E for an electron. And then what happens for the daughter nucleus is A doesn't change, right? Because we have A plus A on the one side here. So A before is equal to 0 plus A afterwards. So our A doesn't change. But our Z is going to become Z plus 1. Z plus 1. And that ends up being because we have on the left-hand side Z, and on the right-hand side we have -1 and then plus Z plus 1. Right? And that's how we end up being able to, how we end up having to add one to that. So what's actually happening, like with alpha decay, it's just basically just like a helium nucleus. It's just expelled from the parent nucleus. What happens with beta negative decay is you actually have in the nucleus, you have a neutron. So we're going to start with a neutron. And it spontaneously turns into three different things. It turns into a proton, an electron, and what's called an antineutrino, which is a V with a line on the top of it. An antiparticle is signified by the line on the top of it. You'll see that when we do the positive electron, which is an anti-electron, what that means. So that line above, like, so V would be neutrino, and V with a line above it is antineutrino. So we have this neutron becoming a proton, an electron, and an antineutrino. And notice that we have conservation of charge happening here, because the charge on the neutron is 0, and the charge, the sum of the charges here, we've got +1 for the proton, plus -1 for the electron, which gives me a charge at 0. Okay, so there's been conservation of charge happening there with that neutron and the proton. The proton is kept, right? And this is why Z increases by 1. So this is kept by the daughter nucleus. So that increases Z by 1. And then both the electron and antineutrino are expelled. The beta particle is actually something that can be detected, or well, seen. The neutrino, the antineutrino is rather elusive, and it's there, but there's kind of a weird history on where it came from. We'll talk about that in a few minutes. Okay, so the nucleus throws out the electron, antineutrino keeps the proton. I didn't realize I had it written down. So what happens here is you move one to the right on the periodic table. So we'll do a simple little example here, just to illustrate beta negative decay. So we want to do beta negative decay for cobalt-60. So cobalt 60, so that's 60. The symbol for cobalt is CO, and cobalt is element 27. It's going to expel a beta particle. So A stays the same, right? We have 60 on the left-hand side. We're going to have 60 on the right-hand side. But we need to add 1 to our Z. So instead of 27, it becomes 28. And element 28 is nickel. Then you also have to add in your antinuclear. Okay, the hazards of beta positive and beta negative are the same. So I'm just going to put it on the one page and we won't put it on the other page. But beta particles, they can travel, they're fairly high energy. They travel at high speeds. They're high energy. High speeds. So they can travel fairly decently, okay? Because they're traveling at the speed of light. They can travel further than alpha particles. And they can penetrate several millimeters of aluminum. Which means they can penetrate into, they can travel several centimeters into the body. Into tissue. So in order to shield beta particles, they need to be shielded. They can be shielded by basically they need several millimeters of aluminum. So a few centimeters, let's say a few centimeters of aluminum are necessary to shield it. Okay, so that's beta negative. So we'll move on to beta positive, which is similar, yet there's some subtle differences, but generally it's pretty similar what we're going to do. I said I had the hazards up here, but I'm not going to talk about the same hazards. So beta positive decay is a positive beta particle, which is a high energy anti-electron, or what's called a positron. Okay, so we signify that with E with a little anti-hat, or you can have a positive electron, if I can say that. But we avoid the positives and negatives in the nuclear notation. So what we have, again, we've got our parent nucleus. It decays and it expels it undergoes beta positive decay. So we still have a zero on the top, but on the bottom now it's a positive one instead of a negative one, and then beta. So then what happens here is the A stays the same on the top, and then we subtract 1 off the atomic number. So then we're moving 1 to the left. On the periodic table. And you should notice that we're still balanced here. A is equal to 0 plus A, and Z is equal to 1 plus Z minus 1. What happens with beta positive decay, when you expel, or when an anti-electron is expelled, is a proton, it turns into a neutron, a positive electron, like a positron, so this is an anti-electron, and a neutrino, not an antineutrino. Just a little bit too about antimatter. We'll talk about it in a fair bit more detail in one of the last lessons in this unit. But antimatter is just, it has everything the same as the matter. So an electron and an anti-electron, or electron and a positron, are identical. They have the same mass, they have the same absolute value of charge, they have the same spin, all that kind of stuff. What an antiparticle is has everything the same as the real particle, but with one one thing that's different. And so in this case, it's the sign of the charge, right? It's positive charge instead of negative. So what happens here is the nucleus throws out the positron in the neutrino and it keeps the neutron. So then what happens here, over here we have a charge of +1, and over here we have a charge of, we've got 0 plus +1 plus 0, which gives us a charge of +1. So charge is conserved there, right? Like you can't have a particle break down into other particles and not conserve charge. It has to conserve its charge. So we want to provide the beta positive decay equation for cobalt system. So same parent nucleus that we had before. So 6027 cobalt. I better double check 27. Isn't that from memory? Yep. And it's going to emit a beta positive particle. So the top number stays the same, 60, but we now subtract 1 off the bottom, so 26, which is iron. And then plus a neutrino. And for hazards in shielding, see beta negative decay, because it's the same. Okay, next page. Gamma decay. I'm missing the stuff that I had in there about the neutrinos. I had a little blurb about neutrinos that I wanted to talk to you about, but I don't have it obviously in here. So I'll have to talk to you about that when we do half-life. I think that's what we'll end up doing. Just see if I got it in here. Basically, it was just basically that, you know, like beta decay seemed to break conservation laws because mass wasn't conserved. The missing mass. If we went back to this when physicists looked at the mass situations in a situation like this, like the mass of cobalt, the mass of cobalt 60 before the reaction should be the same as the mass of all of the products coming out of the reaction. And so before the neutrino was actually discovered, there was mass missing. So they figured there had to be a particle that existed that they just couldn't see because there was mass missing, but it had to be accounted for somewhere. Okay, gamma decay. Gamma is a little different than the other three types of decay because it doesn't actually change the parent nucleus. And then gamma decay is also usually occurs along with other types of decay. It very rarely occurs on its own. It usually accompanies alpha or beta decay. So there's no change to the parent nucleus. Okay, and it usually accompanies alpha or beta decay. So you do it all as one equation. Don't do it separately. It's done as in one step. So you have the parent nucleus, and then how we write gamma decay. A is 0 and Z is 0, and then it's got that funny little upside down fish. So then your daughter nucleus is the same as the parent nucleus, or it's altered as a result of the other type of decay that the particle is undergoing at the same time. I don't know why I left so much space. That's a lot of space there. Not sure what it is I wanted to say. I went back to see what it was. I went back and found my notes on a PDF file. So this was just meant to show that if we have the parent nucleus and we have gamma decay, it will accompany alpha, which then will leave you with A minus 4, Z minus 2 daughter, or it would accompany some kind of beta, either positive or negative beta. So with that, that's how you write it, as opposed to like two separate equations. So we want to do alpha and gamma decay equation for americium 241. Okay, so americium 241. So 241 AM for americium, and americium is 95. Okay, so it's going to undergo alpha decay, 42He for alpha, plus 0, 0 gamma. Plus 241 minus 4 is 237, and 95 minus 2 is 93, and that is neptunium. then just remember, if you did beta decay as well, like you'd have to include the neutrino or the beta negative antineutrino, beta positive neutrino. Hazards of gamma radiation. Actually, I should go back here. Beta negative is ionizing radiation. This is considered ionizing. Right? It alters atoms in the body. Gamma is the same. Gamma is also ionizing radiation. Gamma has, it's like gamma radiation. It's like the gamma from the electromagnetic spectrum, right? So this has extremely high energy, extremely small wavelength and high energy. It travels at the speed of light because it is a gamma particle, gamma photon. They can penetrate about 30 centimeters of lead. And it can travel about 2 kilometers in air. Okay, so it's really, this is the real dangerous stuff, and this is the stuff that we really have to shield against in a nuclear power plant. And that's not because it's constantly producing gamma radiation, that's just in case it does. So shielding, you need about 6 feet of concrete. As you see the cooling towers. Or sorry, maybe not the cooling towers? No, it's not. It's like, no, not the cooling towers, but nuclear power plants have big, like where the reactors are usually huge, big cement silos, because it's surrounded by 6 feet of concrete. And in fact, the cyclotron at the Cross Cancer Institute, they had to build the casing for it first, and then people from the Canadian Nuclear Regulatory Society, something like that, I think that's the name of it is, have come out and inspect it to make sure it's okay to put the cyclotron in, because the cyclotron produces gamma radiation, and before they're allowed to have it. And they had to build this, they basically had to kind of cut open part of the hospital and build a box that was 6 feet, had 6 feet of concrete on the bottom, the top, and all the sides. And then because of where the cyclotron is, like they did that, and then the cyclotron itself, they had to kind of open up the roof and drop the cyclotron in from the top with one of the biggest cranes in Alberta was used to do that because of the weight of it. Sorry, I think it's the box that they should. I'm not quite sure of it. I'm messing up the story because I'm nervous recording the lesson. But it's just interesting, like how much shielding is required for that. So about 6 feet of concrete, or about at least a foot of lead. For the less energetic gamma rays, smaller amounts of lead. Okay, so now we'll just kind of talk about this generally. Now that we've got our 4 types of decay defined, and we know something to do with them, we're going to work with them a little bit. So one thing that you need to be able to do when it comes to radioactive decay is be able to identify the type of decay that's being talked about using one of 2 methods. The first one is penetration ability, right? Because the different radiations penetrate to different levels, right? So this was the alpha penetrates cardboard, or say paper, right? Beta penetrates cardboard, and gamma penetrates concrete or lead. So you can look at that. And the thing is when you're shielding, you always want to shield for the highest level of, you always want to shield for the highest level of radiation. Because alpha and beta aren't require less shielding, but to be safe when you're working with radioactive substance, you want to shield for everything. Of course, now we aren't normally going to be working with this stuff. The closest that we ever come to stuff is the alpha decay in a tool detector. The other way that you can determine the type of radiation being emitted is the way that it deflects the magnetic field. Right? Because an alpha particle is positive and has a large mass. Beta negative is negative and it has a small mass, right, because it's an electron. Beta positive is positive and it has a small mass. And gamma has no charge. So gamma is usually the easiest one to figure out because it's the one that passes through a magnetic field undeflected. Right? It doesn't deflect in a magnetic field. So that's our gamma. Oops, that's a weird symbol. Keep doing that. There we go. So that's gamma. And then we just use your hand rule, right? So the particles might, if I've got my thumb, my finger, and then my palm, okay? So if my thumb is pointing to the right-hand side of the page and my fingers are going into the page. So my palm points down on my left hand and up on my right hand. So that means these are the positive particles and these are the negative particles. So the one that goes down is the negative particle, so that's beta negative. And the two that go up are beta positive and alpha. And the beta positive is going to deflect less because it has less mass, and the alpha particle is going to deflect more because it has a larger mass. I believe there's a question like that in your practice problems that you really should work on because this can be kind of tough, but it's just going back to the previous unit, but those hand rules again. Okay, so then we'll just do a few extra decay equations here just to practice a little bit more for decay. The alpha decay of radium-226. So radium-226, radium is Ra, and it is element 88. It's going to undergo alpha decay for 2He, and we take 4 off the top number, so 222, and 2 off the bottom number, so 86, and I think that's lead, but that's not radon, Rn. That is. Beta negative decay of carbon 14. So 14, carbon is 6. Whoops. Carbon, the symbol is C. The atomic number is 6. It undergoes beta negative decay, so 0, negative 1B. So the top number, the A doesn't stay the same, it's still 14, and we're going to add 1 to the bottom for 7, which gives me nitrogen, plus an antineutrino. Beta positive decay of fluorine 19. So 19F and fluorine is 9. Beta positive, so 0 positive 1 beta plus 19 and then element 8, which is oxygen, plus a neutrino. And then alpha and gamma decay of polonium-215. So 215 on polonium, I'm never going to be able to find it. Oh, 84. Alpha decay and gamma decay, and we end up with 211, 82, and 82 is lead. And that's that. Okay. On to the next little bit. This is just a little bit about stability. So I just included a stability chart that just kind of shows, it graphs. We've got a number of nucleons and a nucleus on the bottom, and you'll see different versions of these. This is the most common, with a number of neutrons plus protons on the bottom of the graph, and then the average binding energy per nucleon is what's going on there. And that average binding energy per nucleon. That's related to how close the number of protons and neutrons is. Remember, stability, an atom is more stable when the number of protons equals the number of neutrons, or it's very close. So as Z increases, as the atomic number increases, as the number of protons in the nucleus increases, isotopes need an increasing ratio of neutrons to protons to be stable. There are no completely stable isotopes with more than 83 protons. So as soon as you go above 83 on the periodic table, everything's radioactive. And stable isotopes have a greater binding energy than unstable isotopes. And on this chart, it's maybe hard to discern from what's going on, but the highest, the element on here, the isotope with the highest binding energy per nucleon, which makes it the most stable element, is iron 56. So iron 56 is the most stable element. And then that just kind of, this just shows some isotopes, and there's some kind of changes and things on here. When we get to fission and fusion, you're going to see a similar chart that then shows you where fission occurs and where fusion occurs. That's all. So this is just to give you an idea of stability, and that there are, like, it's not really one end of the periodic table that's more stable than the other end. It has to do with number of protons versus number of neutrons. Right? And if we think about that with iron, like iron is 26. So iron 56 has number of protons is 26, and the number of neutrons in this case is 30. You know, so those numbers are pretty close together, so that makes it very, very stable. Okay, and the last page of the notes today is just looking at what's called a radioactive decay series. And this is just a different way of showing decay. So sometimes a radioactive nucleus will decay into a daughter nucleus that is also radioactive and unstable. And so when this happens, a nucleus will undergo successive alpha or beta decays until it reaches a daughter nucleus that is stable. This process can at times take thousands of years. It depends on the isotopes and the half-life. Half-life being how quickly something decays, which is what we're going to talk about. Give me a second. Okay, so again, like I mentioned, we're going to talk about half-life next week a little bit, which is how fast something decays. And so this here, what we're looking at here, this decay series here, is the decay of thorium-232. So this shows we have thorium-232, and it shows the decay. It goes through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 decays before it turns into something stable. Yeah, at least 11, if not more. It looks like it goes through quite a few. Anyway, so that's this is just one version of a decay series. Again, you'll see there's one in your textbook. There's also one in your practice problems. So all we want to do here is we want to write specific parts of the decay. So we're going to use the natural decay series to write the nuclear decay equation for thorium-228. So we want to find thorium-228, which is up here, and then write the decay series for that. So it undergoes, like it's losing, so we have A, it starts at 228, becomes 224, Z starts at 90, becomes 88. So we want to figure out, we've got 228 thorium, which is 90 on the periodic table, that's also in there. We end up with 224, 88 radium, and we need to figure out what type of decay that was. So that's obviously alpha decay, right? Because A is going down by 4, and Z is going down by 2. So this is 4, 2, H, E for alpha. Okay, so that's all that is figuring out which the decay is. And you can also get that from the chart, because if you look up here, this is going down. Thorium-228 goes down by 4 for A, and it goes down by 2 for Z. So the next one we want to do is bismuth-212. We want to find bismuth-212. Bismuth-212 also undergoes alpha decay, it looks like. So 212, 83 Bi. And we end up with 208, 81 Ti. Ti? 81? 81 is thallium, TL. TL, and then that's 4, 2, And the last one we'll do is lead-212. Lead-212, so that's here. Okay, lead-212 decays to bismuth-212. So 212, 82 lead becomes 212, 83 bismuth. So we're adding 1 to the atomic number, which means it's beta negative decay. So that means that there's an anti-neutrino that comes out as well. Good. Okay, and that's the lesson, you guys. And now you can look at the rest of the questions under the radioactivity assignment from your outline. So the one I assigned yesterday, page 313, number 1, that's just nuclear notation. Sorry, isotope notation. Then page 315 to 318, numbers 1 to 11, that's decay. That's really the important one to do. And then there's also some questions on hazards and shielding that's interesting to do because they are starting to ask a few more questions with the level. So then that's just the practice problems for you over the long weekend. Remember, you don't have school Monday or Tuesday, so I won't see you now again until Wednesday. Although I'm not seeing you now, I saw you yesterday. It's really today. Anyway, have a really good weekend. Yeah, and have fun with the nuclear decay.